So good morning, everyone. So welcome to this fourth edition of the VPH Summer School. Just before we start, I give you a brief description of what you have in your folder. Practical things. So most important things. So you have the lunch tickets here. So don't lose that. You will need it for the whole week, okay? And then you have the printed program, okay? And so in the second folder, so you have some detail about the different speakers. You don't have the abstracts of the biosketches here. If you want to see the abstract of the biosketches, so you just go into the web page of the VPH Summer School, then you go to speakers, okay? And then you have all the detail. You also have an evaluation form, okay? So please, before you leave the summer school by the end of the week, so we would be very grateful if you could fill in this form and give it back to us. So we take it into account then for the further editions. And so you have also a page so with practical information about the hands-on. So where the hands-on are, so the different rooms. There is a shared folder where you have all the information about the hands-on, so material, etc. You can also leave material here, for example, when you're doing your presentation, the models you're editing, okay? So then there is a path to that folder, and there is also the user information. If you need internet, you don't have it at your room, so we have a Wi-Fi here, which is called UCAETIC, and you will see all the information at the registration desk. Okay, it's on the wall, and with this Wi-Fi, you will have coverage all over the campus. So that's all for the practical stuff. So now I would like to briefly introduce the VPH Institute. So the VPH Summer School is then co-organized by the University Pompeu Fabra and the Department of Information and Communication Technologies that hosts the biomedical engineering degrees and the computational biomedical engineering master. And so we're a regular member of the VPH Institute. We're deeply involved in the student committee, and then so this is why we are now organizing every year the VPH Summer School. We hope to continue to do so along the time. I don't know how many of you know the VPH Institute, but then I would like then to pass you an introductory video of 3.5 minutes.
We all have the same dream, to make in-situ healthcare a reality. But this is something that no one, not the largest company in the world, not the largest academic institution, can do by itself.
The VPH Institute is a society of scientists interested in the use of modeling and simulation in healthcare.
It's one of the critical elements to go to the European Parliament.
It is a mechanism to harmonize the research between the United States and Europe.
Engineers, computer scientists, biologists, clinicians, all working around this dream. Can we predict human health?
I met so many people that did get new ideas on the academic field, how I can solve those problems that urgently need to be solved in cancer.
Being a member of the VPH Institute is important to participate in a network of researchers who share these ideas and want to make them progress.
I constantly learn from my colleagues about how they use modeling and simulation.
I joined the VPH PhD committee. This committee organized all kinds of events. One of them is webinars.
I'm chairing the student committee of the VPH Institute. One of the major activities is as a summer school for students have the opportunity over 1 week to listen to the talks from very accomplished researchers.
It is an important network and a way to create links with senior members and scientists of the community.
I met all these people that are sincerely interested in contributing to actually improving healthcare and not just making a new scientific paper.
I don't know of any other institute that's really trying to bring together both the industry, the regulators, the academic researchers, both in the EU and the US.
It's community, it's networking.
One of the things that we're doing at FDA is trying to advance the use of in silico models and how do we get those models into regulatory applications.
This modeling, we will succeed to overcome the last bad outcome of children with cancer.
And I think the use of computer simulation will allow us in the future to help better describe those treatments that are needed for individual patients.
With the VPHI, we are seeing the researchers are really focused on taking it to the next level, understanding how that impacts the treatment that we give to an individual.
If you are building up models from basic science and the goal is to bring it to the clinic, you need to involve clinicians. They need to translate this to the patient.
We need to have the right policies in place, we need to have the right regulations in place, and it is not something that as a scientist you can do on your own.
It is important to have one voice that speaks up and systematically influence the policy, the industry, the research agenda.
You are also contributing to something that is bigger than yourself, in the sense that you are part of creating momentum. It is a responsibility to be part of this.
This is a revolution.
In silico, medicine will be the future.
Okay, so a friend of mine used to say that everyone believes in experiments except the person who have done the experiments. And no one believes in computational model except the person who has built the computational model. So that's pretty true, actually. You've all had questions about validation, what you can actually do with your model, etc. So that's the objective of this community. This is scientific societies. The VPH Institute is a scientific society. So the objective of this community is actually then to work together, to team up over different subdisciplines of computational biomedical engineering, so molecular level, gene level, so computational biology, bioinformatics, and then higher level tissue constitutive modeling, organ modeling, implementation questions, and of course machine learning is becoming increasingly important and has its place into that. So in order to combine things as much as possible, to have predictive systems or simulation-based descriptive systems that are more and more reliable, and then work on the acceptance, so by the professionals, so healthcare professionals, by the industry, who can then adopt all these technologies and turn it into products that will go through all the certification steps and then gain credibility. And then, of course, one of the basic efforts we have to do as researchers is to work on models that are not obligatorily more and more sophisticated, but I would say more and more suitable for the kind of problems we have to tackle, and more and more credible in that sense. So I have a small presentation of the VPH Institute so that you can see the kind of efforts that are being done in that direction. I'll try to keep it short in order not to delay then the talk of Josep Ma Antó, our first speaker. So you've seen basically then the introduction. Just a few words about the origin of the VPH Institute. So it comes from the will to translate physiology into handable models, where we can play with parameters and then understand the complexity of the physiology. So it's very broad itself. It aims to be descriptive, but with description that we can understand. It aims to be integrative. If we can understand things, so we can integrate the things. and lately attempts to be, of course, predictive up to some point. So the definition of predictive can be discussed. So an important objective is the realization of the three R's. So 3 R's in animal testing, so which is about the reduction of animal testing. So reduction and replacement of the animals, but it is also true for the 3 R's in industry. So reuse, recycle, and reduce. So one of the objectives of the community is also then to be able to share knowledge, not to have to reinvent the wheel every time, and then really build on the work of others. So everyone working in computational biomedical engineering knows that it's very difficult to set up a model from the root. So you spend years, and at the end you just have one journal paper about it. So it can be very frustrating, compared to experiments or to clinical data. So it makes a lot of sense actually to share. So individually, but also community-wise. So everything came from physiology and modeling the physiology. So of course that's a paradigm that was true in 2007, and though the computational approach of physiology remains very, very valid, so now in healthcare technologies, machine learning is increasingly entering, and it has a high added value. And actually there is. So very often we hear about a competition, whether I should go for physiological modeling, which we would call mechanistic modeling, describing mechanisms, etc., or through machine learning, and the extreme version of machine learning then would be the black box. You have an input, you have an output, you don't know exactly what is happening in between. So now with a massive amount of data and with a possibly treatment of data through physiology-based models, we can then simulate different mechanisms. We can see variability among different mechanisms that are related to individual variability of the patients. But there are two problems. The first problem is that when we have a model with 20 parameters, how do we interpret the variability of this model from patient to patient? So here we have first problem in physiology modeling. And the second problem that we have is computational cost. So if you're doing computational biology, if you're doing physiological modeling of tissues and organs, so you can have simulations that run several hours up to several days. So you cannot really build a virtual cohort of patients based on that. So it's actually where machine learning comes. To do a mining of simulated data, to do intelligence sensitivity analysis of physiology-based models in order to extract a relevance that a priori would be very difficult to see in the midst of parameters, variations thereof, and different results. And another great application is actually to grab the mechanisms of physiological-based modeling and then to use machine learning technology in order to learn from these mechanisms. So you don't learn from data, you learn from mechanisms, and then you couple with data. And then you can have a black box, but then with different parameters that have their counterpart in physiological modeling, and you can interpret this black box, okay? So that would be the new evolution of this paradigm. This is why this summer school then wanted to highlight the two parts of computational biomedical engineering, physiological modeling, which we call some mechanistic modeling, and machine learning. So the VPH Institute started from a European project, so strategical project, and then everything was settled and became mature in order to become a community with legal existence, which is the institute. So there are different level of involvements within this community, and so you have high level of involvements that are institutional involvements. So institutions pay 5,000 euros per year choose institutes. They are the pillars of the institutes. They enter into the board. The representatives of these institutions enter into the board of directors and then decide the strategy. Then there's a basic level of involvement or ordinary membership, which is also institutional, but it's cheaper. So here the representative sits in the General Assembly and then also doesn't decide but helps them to discuss the strategy of the community. And then, so if your institution is not covering the membership, so you have two modalities of personal involvement. So normal scientist involvement as physical person, and then you have the student membership. Okay, so if your institution is actually ordinary member or supporting member, so the personal membership is covered by that. So you go into the registration page, and then you select your institution among the list, and that's fine. As for personal and student membership, just to insist that once you have paid the fees for the VPH summer school, so you have 1 year of free membership to the VPH Institute. So you need to go to the webpage, you register, you send then a copy of your registration here, and so then you will have a 1 year membership. Okay. So so the activities of VPH Institutes are focused on 3 groups. So clinical stakeholders, so mainly digital patient technologies, so in order to advise, to predict, so improve the diagnostics, the prognosis, and decision taking. Industrial stakeholders, then in order to translate all this capacity and competencies into products. So it can be commercial products, can be public-based products. So many different options are open here. And then for the citizen at large, that's all what are personal health assistance, so mobile health, etc. So you actually have a lot of technology behind a simple application, and of course all what can be assistance at home, and systems to empower the patients to help to take decisions. For example, if patient has to undergo a surgery, actually the decision of the patient is often more important than the decision of the surgeon in musculoskeletal problem. Okay, so in cancer that might be different, but the activities are the VPH conference, the biannual conference that is growing, where you have actually all the field of biomedical engineering covered. So it started. Actually, the first conference was in 2012 in London. So VPH Institute was not founded at that time. It was a VPH Network of Excellence. Then, so we had Trondheim in 2014, and the next conference will be in Paris in 2020. There is a VPH newsletter where you have job offers, news from the community, you have news from the related industry, etc. And you have the activities of the student committee. So within the activity of student committees, so the 2 main activities are the VPH Summer School, which we're organizing here, and then there is a VPHI webinar series. VPHI webinar series are online webinars that you can follow through GoToMeeting system. You can interact with the speakers. And the objective is actually to have very senior speakers, not seniors in terms of age, but in terms of experience in science, who are people that you would have difficulties to approach in conferences because they're always very busy, etc. So here we basically offer a room where you can then listen to an integrated research story from these people, inspiring, and then you have time without having to rush in order to make your questions and to discuss with those persons. We are now also opening this VPHI webinar series to researchers that are consolidating their research careers. So typically postdoctoral, between junior, senior postdoctoral researchers. So then in order to start to disseminate their efforts to consolidate their research career. And then there is a VPHI, Policy Affair Working Group. That was the initial name. Now it's the Avicina Alliance. So this is a group of experts from the academia, from the industry, that work together with policymakers and regulators. So in order then to find a proper niche of the VPHI technologies, of the PH technologies, into the research ecosystem, into the healthcare system, and to the industrial system. So basically, there already have been early presentation of success cases at the European Parliament, so invited by parliamentaries, and which led then to an official endorsement of computational biomedical engineering technologies for the current framework program. So if you're applying then to European projects, so you can see that in many calls actually computer modeling is here. So this is basically the effort of the Policy Affair Working Group of the Avicina Alliance. Being member of the VP Institute doesn't tell that you will have more probabilities to win one of these grants, right? But then if you contribute to the community, so this is also where you're contributing, not only conferences, sharing, etc., but contribution at a higher level of international scientific strategy. Okay. And so the Avicina Alliance that works closely with regulators, with policymakers, so is half represented by the VPH Institute, which is actually a bunch of academics, and so half represented so by the industry. So now in the industry, so we have relatively important companies such as ANSYS, Medtronic, and contributing in order to cite maybe the two largest ones. And so we have a lot of SMEs as well. As for strategic alliances that have been consolidated over time, so with the European Medicine Agency, with European Parliament, with Food and Drug Administration, and then I have already mentioned, so with the European Commission for funding opportunities, etc. Okay, so I think I have told everything about this. So the only thing is that, so if you have not registered, if you're registered as a VPH Summer School and not registered as a VPHI member, so and you want to contribute to that effort and then benefit of the, and have also the benefits in terms of reduced fees for the different events, access to the newsletter, to the job offers, have the opportunity to enter in the different working groups, and then to interact beyond your academia, so interact with other institutions, regulators, policymakers. So just register. So you support the community, and I think you're also supporting yourself when you're doing that. So now we'll just pass the word then to Miguel Angel, so my colleague, who will introduce then the first keynote speaker of this series. Welcome to the summer school, and I hope you will enjoy it.
Thank you, Jerome. Welcome everyone to UPF. As Jerome said, we are both working in the same group here in UPF, in BC and MedTech. It is really a pleasure to have you all here, and it is really an honor to present the first keynote today. I don't know if we can have already the first slide. I would like to highlight just two dimensions about this talk. First of all, the institution, IS Global. Professor Antó, he's the scientific director of IS Global, and this is an institute for global health based here in Barcelona. As you can imagine, global health means many things and is aimed at making a big impact globally, which means a lot of research on developing countries, a lot of research on policies, environment, issues that are at the heart of priorities, both in terms of political priorities, but also socially and basically life. At a more personal dimension, I would like to highlight the profile of Professor Antó. So he's an MD, PhD, so his background is in medicine. He has been a professor here at UPF at the Faculty of Medicine since 98, if I'm not wrong, 1998. By coincidence, 98 is also the value of his age index, if you look in Google Scholar, which is quite amazing. He has been very, very active in research on, as you see here, on asthma and respiratory diseases, which he will explain very well today. Has received numerous distinctions, medals, locally and internationally as well. Is in the board of the top journals and the top conferences in his field. And overall, I think it's really going to be very interesting to see his presentation. So please.
Well, thank you. Thank you very much. Thanks a lot to Professor González and Jérôme Noilly for the, this seems to, not sure how it works. Yeah, that way. I need help, yes. Okay, thank you. No, sorry. So thanks a lot for this opportunity. Thanks a lot to Professor Miguel Ángel González and Jérôme Noilly for this opportunity. It's really a big pleasure, and I think that to some extent, or to a large extent, probably my presence here is also the result of the context that we have had, the interchange that we have had recently with the team here at the UPF, when we approached them from ES Global saying, guys, we are convinced we need to change our mind and to move to new fields. And one of these fields is probably artificial intelligence and machine learning, and to which extent we can collaborate. And they proved to be extremely open-minded and generous in this relationship that has been lasting for a few months. And I think that that's, I would like to see my presentation here as part of this collaboration. Thanks a lot, because this is an opportunity to share with you. I mean, I'm pretty sure that I should be listening you instead of talking you. And this is because I basically know nothing about mechanistic and machine learning approaches. And then you will see why I am here. I mean, I hope I am here as a bridge between the classical approaches in medicine to the new approaches in what it's called here in silico medicine. So thanks a lot again for this opportunity. Probably a final remark is that this better title would be probably From Populations to Systems to Populations, but I think this is a reasonably working title. So let me begin with this painting of Xavier Valls, who was a Catalan painter. He was born in Barcelona, had to leave the country, Catalonia, because the civil war, and then migrated to France. Finally, he was able to develop a very nice artistic career in France and painted this kind of atmospheres that were, I mean, realistic, but not so much, I mean, post-impressionistic in a way. And I think it reflects the way that I was educated to understand science and to develop scientific understanding of problems, which is, you can identify which is an apple and which is a bottle, but not totally clear. So if you take out your glasses or you are looking to this from too far, probably you may recognize the shape, so you can say what is ABC, but still you can realize that there is need for improving the definition of the images and the recognition of the object. So, I mean, this is science. You can recognize A from B from C, but you can still need to do further work to refine it. And then this is probably my first encounter with science, when after finishing my training as a specialist in respiratory diseases in one of the big hospitals here in Barcelona, and having completed some training on epidemiology, I had the opportunity, was a very privileged opportunity to work in a very striking public health problem in the city of Barcelona. And the striking public health problems, there were epidemics of asthma. And these epidemics of asthma mean that from time to time, from early 80s to you will see late 80s or early 90s, we had people in the city who in a period of few hours had a so strong attack of asthma that they needed to go to the hospital. Some of them needed even resuscitation. There was some death during these epidemics. So there were very striking episodes. In each of these episodes, altogether maybe 40, 60, 100 people, then for a month, nothing more, and then again another epidemic. These episodes had passed unattended for a period of time until a very smart resident in one of the hospitals realized that there was something unique. He went to the literature. At that time, it was not easy to go to the literature, and she described the asthma epidemics in a letter in Lancet. And then at that time, I was starting to develop a department of research in the City Council of Barcelona, which research in a city council was a pretty innovative approach at that time. And then I was, because I had a respiratory background, I had to work with this problem. So I had the opportunity, and this is to make the history short, and then applying medicine and epidemiology, we were able to show that the problem of the cause of the asthma epidemics was this silo that you can still see in the harbor of Barcelona, very close to a very fancy Vela hotel. And this harbor was a recipient for ships unloading soybeans, which is a big product for food market. And these unloadings were producing dust over the city, and this dust was sensitizing people who were allergic, and then these people were developing allergy to soybeans, and then when there was another unloading, there was an epidemic of asthma when the climatologic conditions were appropriate. Well, the nice thing it was that we were able to apply traditional epidemiology, and this was my first international paper, a paper that I was able to write in a weekend, something that never happened again. So you may call it inspiration, I don't know. I mean, and this paper was a paper saying there is an asthma epidemic. This is epidemic. This is not chance. There is geographical clustering. This geographical clustering is near to the harbor. It should be something in the harbor, but it took years to identify what was in the harbor. Once we had an hypothesis of the soybean, that it will be too long to explain, we were able to then produce simultaneously one case control study showing that the asthmatics that were attended in epidemic days in the hospital were, most of them, sensitized to soybeans, whereas asthmatics attended in the same hospitals in non-epidemic days were not. And the other paper, there was a paper in Lancet and New England, where and still are probably the more cited journals in medicine. So we had this opportunity of publishing. This never happened again, to publish two papers simultaneously the same week, one in Lancet, the other in New England, with editorials. And the paper in New England was a paper showing that there was a time series study looking to asthma days and unloadings, yes or not, many different products, and showing that there was a very strong and quantifiably high association between soybean unloadings and asthma epidemic days. And then that was considered a very strong causal evidence. It was enough to convince authorities with some legal pressure to put filters in the silo. And after they put filters in the silo, in '93, we published another paper in New England Journal of Medicine showing that the asthma epidemics had disappeared, and indeed even asthma in the intensive care units of the Barcelona hospitals disappeared. So 90% of asthma in the intensive care units of the city at that time were due to asthma epidemics. This was a very timely development because the city was going to host the Olympic Games in '92, and it was at some problem concerns that this issue could make some problems for the Olympics, and I think we were able to make a solution for that. Going back to the Xavier Valls, I mean, this is a very crystal clear results, but there's plenty of things that we were not able to explain. And for instance, why the asthma epidemics never affected children in the city? And we still don't know. So this is still pretty clear results, but still always, as always in research, plenty of big questions that we cannot understand. By the way, it was demonstrated that the same had happened, although it was unrealized, in New Orleans and in other harbors in the world. And nowadays, it's a routine monitoring system in the Barcelona city to assign filters every week in the city to keep control of the soybean allergen. So if any of you is allergic to soybean, don't worry, the levels are maintained pretty low and the risk of having an attack of asthma due to soybean is negligible. Well, having had this success in resolving asthma, let me go one, then let me, there was a question I wanted to make you at the beginning, I forgot, that it's to calibrate our distance or connectivity. It's how many of you have medical background or medical experience? 1, 2, 3, okay. And many of you have 5, okay. And how many of you have experience or proximity with epidemiology? Okay, so we are pretty distant, okay? So don't hesitate to make me questions of all types during the presentation. Well, this is asthma. Asthma, it's a disease that it's a chronic inflammatory disorder. It probably may persist for the life, though you may pass long periods without symptoms. It's probably the result of many different cellular types who have orchestrated interrelationships and maintain the inflammation. It's associated with one of the landmarks of the disease, that is bronchial hyperresponsiveness. So suddenly the bronchial tree may bronchoconstrict, so because the muscle, the smooth muscles in the bronchial tree, and then you may have shortness of breath suddenly or very rapidly, and this again may resolve with adequate treatment or with preventing the exposure to the triggers. It may affect of the life cycle. It's a very common cause of disability-adjusted life years, and remarkably has shown a worldwide increase since the 70s. So before 70s, in many countries, it was very low prevalence, below maybe 5%, 3%, 1%, and has increased double, triple, increased by fourfold in some countries to become a very common disease. After having worked in the asthma epidemics, a word that I probably need and this is allergy. An allergy is one of the characteristics of asthma. We can talk later on how much asthma is allergic. Indeed, we don't really know, I think. But one of the ways that we measure asthma, this is the painful way, which is the skin test. So you are put bit drops of allergen in your arm, and then this is compared with histamine as a negative control, and then you can realize the allergic reaction. You can measure this in millimeters, and you can have a good score of your allergy. Alternatively, you can measure the circulating IgE antibodies to these allergens in the blood, and there is a good correlation in general, although they are not the same, between circulating IgE antibodies and this. And with these symptoms and this kind of a skin test, we use to diagnose allergic asthma in a way or another. Okay? Well, I say you that asthma started to increase in many countries after 70s. And here you have a lot of variability, by sure that there is measurement error and random variability. But you can see that in overall, asthma and atopy, this is asthma in the left, this is atopy, it means positive skin test or positive IG. Both have increased a lot from 70s to the 2000s in many countries of different types. And even in the countries where the prevalence was very low, has been increased in most of them with very few exceptions. Well, this slide, it reflects a sentence that has become very common, that it's the epidemic of asthma. But you see that it's a different epidemic of asthma than the one that we show you. However, with the ingenuity of a young researcher at the time of the asthma epidemics, we thought, guys, if we have been resolving the soybean asthma epidemics, why are not going to resolve this worldwide epidemic? And then it may be similar things. It should be allergens that have been widespread over big cities and producing an increase of asthma. And then we started to do research of asthma. And we became very involved and specialized in research of asthma. But then the things were proved to be much more difficult with the soybeans. And we were totally unable to show that there was a causal relationship between exposure to allergens and asthma in the way that you saw for the soybean epidemics. And this is a paper in the 2000s and was a longitudinal study in children measuring at different age periods of follow-ups in this cohort, the proportion of cohorts with current WHIS in children that were high or low to house dust mite. So house dust mite was probably the first candidate to explain part of the epidemic of asthma. So through indoors and urbanization, we became more exposed to house dust mite. At the early life, you became sensitized, and then you develop persistent chronic inflammation, and you have asthma. But the research failed to show that there was a causal relationship in prospective studies. And indeed, there were randomized control trials showing interventions who reduced house dust mite, and there was no difference in the incidence of asthma after interventions. Well, when you became a specialist in a field, it's very hard to accept that you are not going to solve that, so we did a lot of efforts, and this was our elaboration in our own cohorts, showing that, well, it's a Feldy one, that it's cat instead of mite, and this is symptoms of asthma, and this is a GAM model, and this was again a longitudinal study, and this GAM model, we suggested that there was a complex relationship with maybe an increased dose response at the very low levels of allergen, and then flattening the response up. And we say in the conclusion of the paper, so it's probably, we have failed to show that, we have failed because it's not linear, it's probably a complex dose-response relationship, may vary from one place to another, and may vary from one allergen to another. And this may be a relatively elegant explanation, but when you go to the pictures of the Javier Valls, you say, no, not very convinced that this is the explanation. Well, this reflects my pathling understanding of the problem. So very good evidence that exposure to mites leads to sensitization, very good evidence. Good evidence that if you are sensitized, you may develop the disease, strong longitudinal studies. Good evidence that exposure leads to aggravation if you have the disease, but no evidence that exposure to allergens is causally related to the development of asthma in a longitudinal model. And then, after having reviewed a lot of the literature and spending years on that, I brought this short paper, this letter in Allergy in 2004, where the main conclusion was, I'm sure that the answer of the asthma epidemic is in the data that we have in our cohorts and in our studies, but we need to look to the data with different eyes. This is not going to be the solution. At that time, I can tell you I was very ignorant about. I mean, artificial intelligence, I think, was not in the papers probably at that time yet, in the newspapers that we read, but I was pretty sure that there was a problem of complexity, and this was not going to be solved using traditional epidemiology. So this is how I started to change my mind. Here I say, well, it's probably a conundrum, it's probably a cluster of unsolvable problems. We don't have a satisfactory causal model, as you saw, but we don't have a satisfactory definition. We don't understand the course of asthma. We don't understand the allergy mechanism. There are no satisfactory preventive strategies. So this is a slide that the specialists in the field usually don't like because it's too pessimistic. But if this was my own appraisal and a sufficient reason to say, well, we need to look the data with different eyes, and we are not going to spend the full life dealing with these problems. And then you move to a different type of image reconstruction. So you are not longer able to see what is a bottle and what is an apple, and then you feel lost with the data you have. But art is very useful because art is a different approach. It's free from the experimental restrictions. It's plenty of freedom. And this is what the abstract painters came in the history of art. They start to see the reality in a different way. And this, as you see, is an apple in blossom. So it's not the apple of Xavier Valls, it's the apple of Piet Mondrian, who was one of the pioneers of the abstract act. And then you need to change the way that you see an apple is an apple, and then you need to see things in a different way, and then still you can recognize an apple. And in a way, it was my way in trying to change my ideas, and probably the best concept of the type of approach that I was looking for was this paper and other previous works by Barabasi. I'm sure that many of you probably know Barabasi, and the concept of network medicine. I was very excited reading this. It was for months. It was my main readings was about network medicine. I was very lucky to have a neighbor in the 4th floor of my building that was Ricard Soler. That was the director of the department of the lab of complex systems in the UPF, who is a pioneer of network science. And also, having been exposed to a couple of very inspiring lectures from Luis Serrano, who is the director of the Center for Regulatory Genomics in Barcelona, which he made a presentation of system biology. It should be now about 50 years ago, and I left the presentation with a sense of humiliation as an epidemiologist. Oh my God, the methods we are using, logistic regression and Cox model and longitudinal statistics, we need to change our mind. And then it's just step by step, I was being a bit more familiar with these methods, being totally ignorant, I insist on that. And then you need to have an opportunity. And the opportunity came to me in a way relatively unexpected. That was a call in the FP7. It was a call in a topic on system medicine. And there was a specific call for projects to apply systems medicine to understanding of the allergic diseases. I can promise you that I had no influence on formulating the topics. So other people did, I don't know who. But when we read the call, we say there is an opportunity for us here. We probably know enough about allergic diseases. We know about all the different approaches that we can contact and build up a consortium. The only restriction was that there was a relatively well-funded project. It was 12 million, but there was only one, yes or no. And this is very challenging. And then I was happy to, at that time, receive a call from Professor Jean Bousquet from in CERN in France, who is a very worldwide expert in allergic rhinitis and in asthma, who called me, Joseph, I'm thinking about, we had never done research together before. He called me, we are doing research. We're thinking to develop a consortium. Would you like to talk about that? We had good understanding. Then we were aware there was a very good consortium of German, British people, very good colleagues, giants in the field that were competing. We had a conference call to put together. They say, no, we go by ourselves. So we went to the call, and then we were enough lucky to win the proposal. And then give us a totally different opportunity. It was the first time that we had said how we can move from traditional epidemiology to the systems medicine approach. So this was the general aims of the medal. It was a huge work. There were nights and nights, sleeping a couple of hours, but we did it. Just generate novel knowledge for the mechanisms of allergy from early childhood to young, develop a novel definition of phenotypes with an integrative approach, understand how a network of molecular and environmental factors lead to the complex allergy. And you have here some papers that we produced at the beginning of the project. We had the first paper. One of the characteristics of Professor Busquet is he's really, his bibliometric profile is really impressive. He's the 100 more cited papers in the history. I have no one in the list, but he has 8 papers, okay, in the list of the 100 papers more cited in the literature on asthma. And one of his characteristics is that you need to publish everything you do as soon as possible. So the project started in 2011, and we had the first paper, the project description, in 2011, and the knowledge base published in 2012. And then here, this is important because this is the consortium. And here you came to a very challenging issue, that is the multidisciplinarity, how you engage with other disciplines in a dialogue that is enough coherent to build up a research consortium. There was a first work package that I was the leader, the classical and novel phenotypes. So this was my role, redefine how we define asthma and rhinitis and eczema in a different way, using data from birth cohorts, so tens of thousands of children in Europe that have been followed up since birth until, in some cases, adolescence or beyond. Both types of birth cohorts, allergy characterization of allergens, Rudi Valenta in Vienna, epigenetics with the lab of Dirkie Postma in Groningen, proteomics, Stefano Guerra was with us at that time, is now full professor in Arizona University in Tucson, system biology, the group of Charles Offray at that time in the CNRS, and then confirmatory animal models, in vitro human immunology and translation integration into healthcare. Well, this type of, you know that these European projects are very prescriptive. So these are things that you need to do by design because they are in the call of in the writing of the call, and you need to apply of this. But this is a big, like a bubble, making all this to function. It's a real challenge. And then I can tell you that during 6 years, I felt most of the time lost in the middle of the project and how to navigate from one field to another and putting the people together. So it's really challenging. This is the group. This is Professor Jean Busquet. This is Jordi Sunyer, who is Jordi Sunyer. I was maybe early 30s when I started the asthma epidemics, and then the first grant I had for a PhD student, then Jordi came to knock my door, and now Jordi, it's a giant in the field. He has had the recently second year C advanced grant, so it's plenty of very good people here. And this is regarding to the work package 1, how we did conceive the redefinition of the phenotypes. And then we say, well, we are going to use data from the birth cohorts. We are going to enrich this data with new follow-ups and new technologies, but this will be our backbone. This will be our lab, the birth cohorts, tens of thousands thousands of children in different countries in Europe for which we have very accurate and maintained data sets. And then we are going to different things. We are going to review the classical definitions. We are going to sit together with the experts. We are going to rediscuss the definitions, develop the definition of the classical phenotype, and then we are going to select these phenotypes in these cohorts. And then a novel targeted approach. We are going to forget the experts and what they say, and we are going to treat the data that we have with a statistical modeling and looking for clusters of phenotypes and selection of phenotypes. And this is the second part. we are going to use mechanistic data, IgE and IgG arrays, epigenetic, proteomics, transcriptomics, both for the classical and both for the novel. And hopefully we are going to identify fingerprints, we are going to validate, replicate, confirm in animal models, confirm in vitro immunology, and then integrate all this, okay? And I think that this is still a very good and a very nice concept, but it does not work in the context of a 4 years project. It's too short. You need 10 years for this. And the consequence of doing this in 4 years is that you need to do fragmented pieces of this map. What I'm going to show you is basically the phenotypes here, but there's many other papers. We have now published more than 30 papers from this study. And then I will go back to these issues. So the first thing started when we started the project, we did something that it's a challenge. How we can get a database that can be ready for analysis in 1 year. If you expect to have everything integrated, curated in a consortium, you spend the 3 years. And then what we did was to bypass the protocol that we had, that we did apply it indeed, but we bypassed to have an early database. And with this early database, we started to try to think in a different way. And then we realized that there was plenty, hundreds of papers about the prevalence of allergic diseases in children, but we were surprised that there was one particular thing that was not well addressed, and it was the multimorbidity. Very frequently, these diseases go together. But the analysis that we found in the literature, and we found dozens, were Venn diagrams. And Venn diagrams showing the overlap. Even the papers with the Venn diagrams did not care to prove whether the overlap was what you expected by chance or not. And by the way, when we went to the software for the Venn diagrams, we discovered that the available software for the Venn diagrams was not developed for modifying, resizing the overlaps according to the random expectations, to the random distribution, to the null hypothesis, okay? So we develop an analysis to see with canonical approach, so our methods, is really an overlap of these diseases beyond what you would expect by chance? Do these diseases like each other enough to go together much more frequently than you would expect by chance? And then we had these data sets, 12,000 children in young cohorts and more than 20,000 children in all birth cohorts. We had to put all this together. In parallel, we started a follow-up integrated for 13,000 children at the age of 4 and 18. And then these are the distribution. Here is a cohort in USA, but most of the cohorts were in Europe, and you see that there is very wide distribution. And these were our local cohorts. The leader of this cohort was Jordi Sunyer, that has done a big effort in Spain in developing these methodologies. And then here you had what we did. So the objective was to look, are these diseases going together much more than you expect by chance? We did cross-sectional analysis with 16,000 at 4 and 11,000 at 8, and we looked for the prevalence of the expected frequencies for the combinations of diseases, assuming independence of the phenotypes, that we measured through the relative excess and the absolute excess of comorbidity, observed by expected, observed minus expected. We looked at statistical significance through standardized residuals of the chi-square, and then we did longitudinal studies using log linear regression models. And obviously, we included IgE, that is supposed to be one of the main mechanisms of allergic diseases. And then here you have basically the results. This is the prevalence of diseases. So you see children, only asthma, only rhinitis, only eczema. Eczema is allergy in the skin. Rhinitis is allergy in the nose. And then asthma in the lungs. And then this is only asthma at the age of 4 and at the age of 8, only rhinitis. And then asthma and rhinitis, asthma and eczema, rhinitis and eczema, the 3 diseases. And this is the overall comorbidity at these age groups. And then what you have here is the absolute excess of comorbidity and the relative excess of comorbidity. And what you can see, this is the absolute, so it's observed minus expected. This is observed the ratio, and you can see that with the both indexes, yes, these diseases go together much more than you would expect. And they go together for all combinations of the three diseases. Okay? And this is for the ratio statistically significant, with the exception, which is probably something to keep in mind, for rhinitis and eczema. For the rest, the departure is statistically significant. And then we had the opportunity to say, well, IG is supposed to be very important. Is this different in IG positive and in IG negative? So in atopic and non-atopic, or for you, in allergic and non-allergic with the traditional definition. And what you see is no, it's the same. So both in the children who go to the physician, have a skin test, or IG, and they are negative, not allergic. These diseases, not allergic, go together in the same way that in diseases with IG. You can have the feeling that this is higher than here, but this is, you need to take into account that this is observed minus expected. Allergies, this IG is very associated to asthma, so here the ratio, the denominator of the ratio is higher in IG than in the non-IG, so the ratio tends to be higher in the non-IG than in the IG indeed. Then we did the longitudinal model. We took all the children at the age of 4, and then for all these children, we had data at the age of 8. And then we looked how much one disease at the age of 4 increases the risk of multimorbidity at the age of 8. Okay? And then you have here relative risk. If you have asthma only, you have 12 times higher probability to develop a second disease compared to those who have none. And the same for rhinitis, a bit less for eczema. You have asthma and rhinitis, the relative is 40, 40, 36. And if you have the 3, 63. Obviously here, there is a limitation that it's we had no sufficient sample to separate in the outcome the different groups. So the outcome here is multimorbidity, 2 or more diseases, 2 or 3, okay, together, because we cannot separate that. Obviously, if you have multimorbidity at 4, what this tells you is that you are retaining the multimorbidity at 8. But then you can do another thing, that is to exclude all the children with comorbidity at 4. And then you live with 5,000 children. They have allergic diseases at 4, but they have only asthma, only rhinitis, only eczema. And you can see that the relative risk is 7, 7, 4. So you have 7 times higher risk of developing another disease if you have asthma, if you have rhinitis, and 4 times higher risk if you have eczema. And then in this model, that it's a log linear model, IgE is an independent predictor of multimorbidity. So if you don't have any of this, but you have IgE, you have a relative risk that is similar to these diseases. Okay? So it's an independent predictor, but the multimorbidity is present irrespective of IgE. Okay? So this was what we published in this paper that very soon became a highly cited paper in Lancet Respiratory Medicine. And then we say, well, now let's go to forget about experts. We assume that we don't know what is asthma. Okay? So we are not going to define what is asthma, rhinitis, and eczema. What we are going to take is all the 25 symptoms we have in the database, plus all of the variables, age, sex, sensitization, social class, education, country, all the information. And then we are doing cluster analysis. And then the expectation is, will the cluster analysis separate these as different diseases? That's what we expected. Okay? Then the result of the way we're using cluster Cummins with the stopping rule Kalinsky-Karabas, 17,000 children at the age of 4, 14,000 at the age of 8 from 7 birth cohorts, and then covering symptoms, doctor diagnosis, age of onset, treatment, IgE sensitization, weight, height, and other measures. And then after a lot of analysis, the best was very obvious, very clear that the best model was the one that separated two groups of children, not more. Any forcing the clusters beyond two groups was was losing goodness of the model. And then these two groups was a group of 70% children. You have here about 20 symptoms, including IgE, and you see that in the group, 70% of children, low prevalence of symptoms. This is from 0 prevalence to 80% prevalence. Group 2, at the age of 4, they have wheezing, they have bronchial, they have cough, they have nose, sneezing or blocked nose, ever in the last 12 months, they have skin. So these children have a higher prevalence of these 3 diseases in a way or another. And the same at the age of 8. 2 groups, 80% here, 20% here, and then even higher prevalence than here for the 3 diseases. So what the analysis tells you is that cluster analysis with this information cannot separate the 3 diseases, and they put the diseases together. This is a table that compares the canonical approach with the unsupervised approach. And what you have here is asthma, rhinitis, and eczema, the 2, and the 3, defined according to the canonical, and what is their presence in the unsupervised groups. And what you can see here, interestingly, is that all the multimorbidity goes to group 2, except 8 cases of asthma and rhinitis. All the others group 2. However, when you look to asthma, most of asthma goes to group 1. It's defined as a normal group. Cannot separate the symptoms from the general population. Relatively the same for rhinitis, and much less for eczema. Okay? Well, the limitation of this analysis is that the symptoms, in a way, have been defined by experts. So with the symptoms, you are carrying the expert definition, so this is not totally unsupervised. Well, this is the nice thing of the multimorbidity. At that time, machine learning for us was still a very unknown field, but there was a young junior researcher in Ghent. He was doing animal models, but in one of our sessions, he said, well, I know a lot about machine learning because I did most of my PhD with machine learning. He came to spend a few periods with us and develop a very extensive sensitivity analysis of this unsupervised model using self-organizing map, using comparing k-means and hierarchical, looking for the cluster stability, tracking plots, and the results were very consistent, okay? Again, so we published this saying, well, the unsupervised supports the idea that these diseases go together. And then, in this context, we did another thing that we thought it was a complement. And here, because I think I had the feeling that we were moving to in silico medicine. Okay? That with this data, we went again a couple of floors up in our building to meet a group of bioinformaticians. That is the group of Professor Baldo Oliva and Daniel Aguilar. They have been developing network analysis in biology, and then we sit with them and we suggested them. We have shown that these diseases like to go together, both with canonical and unsupervised methods. Can you develop an in silico model to see if these diseases share genetic determinant genes more commonly than you would expect by chance? And they did. Okay, so we were discussing the protocol. Again, it was an opportunity to learn from them. And then they identified the proteins common to asthma, eczema, and rhinitis, looked to the interconnectivity, looked to the cellular pathways, and even predicted proteins performing a network-based analysis. Here I cannot go to the details by ignorance, but basically what they did basically was to go to the genetic databases, basically to OMIM, Ensemble, and the CTD, the Comparative Toxicogenomics database, and to look for all the genes that have been reported in curated databases as associated with asthma, eczema, and rhinitis. then from the genes to the proteins, then they develop the network of the protein-protein interactions, they measure the connectivity between these different genes, and then they look to the cellular pathways and the connectivity of the cellular pathways. They show that there was much common genes than expected. This is expected random assignment. And this is the percentage of the common proteins. In total, there were about 200 proteins related to asthma, about, I think, about 35 related to rhinitis, and about 20 proteins related to eczema, more or less. And then you can see that for all the combinations, there is a match and is a statistically significant increase in shared genes compared to the random expectation. We had a lot of discussion. For instance, we developed 2 null models for random expectation, one with all the proteins in the databases, with all the genes, and the other with all that have been associated to immune diseases. And results were very consistent for both. This is the list of the proteins that were common in asthma, eczema, and rhinitis. So you see which one were common for pairs or for the triad. And then they developed the network of these proteins looking to the interactions. This is for asthma, for rhinitis, and this is for eczema. And this analysis showed that there were 5 proteins, EL4, EL13, EL1, EL1, 18R1, and TSLP, and 2 pathways, AL4 and GATA3, that were common to the 3 diseases, and probably good candidates to explain the connectivity between these diseases. After having spent 20 years exposed to molecular biologists and immunologists of one cytokine and another cytokine, and I should confess that this is the first time that I felt at home dealing with proteins and genes. It was a way of thinking with these guys in bioinformatics that for us it was a natural way of thinking. And it was really interesting. And this is the network for the 3 diseases where you can have in different colors the genes for asthma only, eczema only, rhinitis only, and the ones that I mentioned for the asthma and eczema, asthma and rhinitis, and the 3 diseases together. And then it was also the possibility of looking to the connectivity as you do in a network analysis. And again, you show that the connectivity, they share more genes than expected by chance, but the genes that they share are more interconnected than you would expect by chance, both things together. Okay, and these are some of the cellular pathways, as I say, basically the more important, AL4 and GATA3, explaining the tendency to go together. This is a bit of a reconstruction of the 3 studies, that is asthma, eczema, and rhinitis coexist in about 5–6% of children at the age of 4 and 8. The clinical expression shows a large overlap affecting 30% of children in the general population, 30 at 4, about 20 at the age of 8. And we consider that these 20–30% of children are the ones that are at risk of developing multimorbidity and allergic diseases all over the life cycle. And this multimorbidity pattern is not attributable to chance and likely due to selection bias. The fact that these diseases share a large number of proteins and interconnectedness supports the biological plausibility of a multimorbidity syndrome in allergy, and it suggests that it's type 2 immune responses that are key cytokines dysregulating the network and leading to the multimorbidity, both in IgE and non-IgE children. Can this be taken as the basis for a unifying allergic phenotype? Perhaps. At the population level, these diseases are better classified as a single group than as 3 different diseases. It's not influenced by IgE sensitization. 99% of children with multimorbidity are in symptomatic group. 40% of children with only one disease, compared to 40% of children with only one disease. And the results support to the concept of a unifying phenotype. Well, this last sentence is totally against the mainstream in the field. So the mainstream in the field is, if you want to understand these diseases, go thinner and thinner and thinner and thinner, until you have almost univariate associations between a gene and a phenotype. This is the main reasoning, okay? I think this is important, and this is an area that should be maintained, but at the same time, the field has failed to understand that the multimorbidity, understanding the interconnection between diseases, is a huge opportunity for developing understanding of mechanisms. This is just the last 2 slides. This is a paper that has been sent. We had also expression analysis in a small group of children, a few hundreds of children. We had gene expression, and then we have now finished and submitted the paper doing transcriptomics. And this is basically an analysis in the medal cohorts from whole blood of 786 children and adolescents in 3 European birth cohorts, one of them the cohort in Barcelona. And we have associated to a cohort in Puerto Rico for replication. And then we have considered asthma, atopic dermatitis, and rhinitis according to experts as either single disease or multimorbidity compared to no allergic disease in this 700 and in the, I think this is about 900 in the Puerto Rico cohort. And we have identified 54 genes that are differentially expressed in allergic diseases, including 34 that have not been reported in allergy. And then very interestingly, 8 genes are consistently overexpressed in all combinations of diseases. And these are the 8 genes. Some of them were highlighted, this one in particular highlighted in the in silico model. And all the genes that we had the opportunity, the 54, maybe about 30, that we had the opportunity to replicate in the Puerto Rican cohort, all but one were overexpressed in children with asthma or multimorbidity in the Puerto Rican cohort. We validated the gene expression with RT-qPCR, and then 27 of the 54 genes were differentially expressed in rhinitis alone, and none one overexpressed in asthma or dermatitis alone, which to me it's a very unexpected result. We need to see how we manage. One of the big hypotheses of one of the big obsessions of Jean Bousquet has been that if you don't have rhinitis, you don't have asthma. I never took this too seriously, but I think I need probably start to take it seriously. And then we identified the protein interaction network in this expression analysis and identifies AL5, AL33, that again is Th2 pathways, maybe the relevant for the multimorbidity. So the paper is now submitted. I express that, and I finish with few papers in the literature. So this is a paper based from many different surveys in the world, and you see this is the prevalence patients with multimorbidity. And you see that at the age of 80, you have 80% of the people have more than one disease. So multimorbidity is very common. Grow-ups with age and increases with socioeconomic status. So red line is people with lower socioeconomic status, black is people with higher socioeconomic status. Our belief is that this is wrong, and because they measure multimorbidity based on the conventional definitions, but we believe that multimorbidity is very common. As we have shown, probably 30% of children measure allergic diseases at the age of 4. Okay? So we believe that multimorbidity biologically and environmentally begins early in life, and it probably persists all over the life cycle. However, this is still, now there has been a call for multimorbidity in the Horizon 2020, and we have presented a new consortium for multimorbidity. We will see. It has been a lot of work, but probably we are going one of the few consortiums probably in looking to multimorbidity in children. And this is because the people don't think about multimorbidity in children. Okay? So the other, this is a very good paper from another group. This is 2 cohorts in UK, the MASS cohort and the Avon cohort in UK. Again, they have data from year 1, 3, 5, 8, and 11. And what they have done in this database is Bayesian machine learning methods, and looking to latent class, to dynamic latent class groups. And we sent a letter saying we don't agree with your conclusion. We love your paper, but we don't agree very much with your conclusion. And I will tell you because, well, this is the classes that they find. And you look, no disease, 50% of children, which is not far from our 70% in the unsupervised analysis. And then 3% is the atopic march. So the atopic march is, again a linear deterministic construct. Okay, so you start with a skin at the age of 1 or at birth, usually by food allergy, and then you develop asthma and rhinitis at different age periods. Well, 3%. Persistent eczema with wheeze. Wheeze is, so it's wheezing without effort, and this is a symptom of asthma. 2%. Persistent eczema with late onset rhinitis. Persistent wheeze with late onset rhinitis. Transient wheeze. Eczema only, rhinitis only. So you see that this group, this group, this group, and this group is multimorbidity. Okay? And you have here the groups with only. So you see that at least 5, 8, 10, 15% of the general population of these children have multimorbidity. Well, interestingly, and I must confess that this I realized when I was just preparing the last time the slides for the session, I realized, wow, there is no asthma alone. So maybe Jean Bousquet is right, okay? There is no asthma alone here. I mean, I don't know. This is consistent with the transcriptomic data that I showed you in the last analysis. And then this is just methodological. And then I go back to the network medicine. So I think still we have not yet proven in a sufficiently comprehensive way which is the network of proteins and environmental factors that produce the multimorbidity of these diseases. And I think that it's because the methods we are using are still probably not enough refined. I think that the group that is more advanced in developing the diseasome is the group of Barabasi. Probably what we have done is not far from an in silico analysis that he has done, looking to the asthma in the diseasome, in the complete interactome. And what he has shown in this paper is that there are 3 diseases that go together with asthma due to the interconnectedness of their proteins. And these diseases are Crohn, it's an autoimmune disease, maybe very disabling. Hashimoto, that is an autoimmune disease that may affect the thyroid. And multiple sclerosis, that is a very disabling neurological disease. Interestingly, one of the hypotheses that we have developed in this new project is we are going to look not only the allergic diseases, we are only to look again also for neurological diseases and cognitive disorders. We are not approaching cancer, but we may look to other diseases. So the message here is, yes, these allergic diseases go together, but they don't go alone. They go with other non-allergic diseases. And some of these diseases, the interconnections may be established early in life, and it may show up phenotypically at the end of life. So 2 final slides to conclude. Mapping the heterogeneity and multimorbidity of allergic diseases using the genome phenome information to identify the individual trajectories throughout the life cycle. This is what we want and need to do, mapping this heterogeneity, and we have not mapped the heterogeneity yet finely enough. So this needs further work. Second, we need to develop an integrative understanding of the mechanisms linking the environment with the genome. And this is still a challenge. We have had the opportunity to look to air pollution and smoking, and they are not strikingly predictive of multimorbidity. They are probably related, but not in a strong way, so maybe interactions are much more complex. And finally, we need to apply these concepts and findings of the system approach to develop predictive, and therapeutical strategies. Regarding to prevention, the most the worst consequence of our failure in understanding the causes of asthma is that we have no one single preventive approach to recommend, which is, for me, I describe my research in asthma as a failure, okay? As I see it. The other is to develop predictive, because you start having symptoms in daily life, and the symptoms may persist for the rest of your life, but in a large proportion, probably will disappear in adolescence. We still don't have, we have published a systematic review of predictive methods. Interestingly, one of the few predictors of asthma is rhinitis. So the models don't predict well, but one of the few variables in the models that predict something, it's rhinitis. So we need to develop predictive models. If in few years we can tell the children and the families how this asthma is going to be in 5-10 years, this will be a big change in the clinical setting. And then therapeutical strategies. For therapeutical strategies, now we are in a new era of biologics, so these drugs that are designed with monoclonal antibodies to target specific genes or proteins, and there are two antagonists of interleukins 4 and 13 that have shown in clinical trials to be effective to reduce asthma and, interestingly, I don't remember if the other is eczema and rhinitis, but one of the other two diseases. So I'm sure, well, these trials have if effective, but it's in a limited number of patients. Probably this is an area that will be expanded with more biological knowledge. And then let me to finish here, okay, going back to picture. And then I think I have the feeling nowadays, probably too late, that I have in a way reconstructed my capacity of the Xavier Valls painting at the beginning of the lecture. So I think this is Miguel Barceló, one of the probably more important live painters in the world, to my view. He's a big innovator. This is one of the series that he painted in Mali. He spent a number of years painting in Mali until the violence and the war would make it too risky. And this is women doing agricultural work. And I mean, it's, I think at the end, abstraction, it's a step. But as humans and as societies, we need to diagnose diseases. We need to predict diseases. We need to treat diseases. So in a way or another, we need to decide what is a disease and what is to be treated and what is not to be treated. This needs, again, to move from abstraction to neo-figurativism or realism or whatever you want. Thank you very much. This is the people that you have seen mentioned during the presentation. I think still we have a few minutes for questions, right?
Yes, thanks very much for the presentation. Indeed, we have time for questions. So if anyone wants to do the first question. Yes.
Thank you very much for this really inspiring and interesting lecture. We are doing some machine learning and research in cardiology. And why I want to mention it is actually that with the approaches that we are taking, which is based on trying to order individuals regarding the similarity in measurements, one of the things that we see is that, as you say, there is no single disease. When you start to look at all these patients, what you see is that it's a continuum from totally normal to totally diseased, but there are no clusters in itself. So I think this is indeed an approach that we start to see, or a conclusion that we start to see when we start to look at this data, which I think is very important. And this is indeed a new way of looking at it. But partially related to that is, I think you're also, since you're looking at children and so on, so a big question in all of these things is like, what is related to the base genome? What is related to the in utero exposure of mother or fetus? What is related to the children itself? And where should we start looking and what should we look at?
Yeah, this is really a critical question. So what I presented is extreme simplification, and but where is the environment and where is the epigenetics, where is the chromatin modification, and all these things. And I think this is part of the work that needs to be done. Here, I mean, one of the big challenges is in this type of approach is that we have tens of thousands of children for which we have symptoms repeated, but we don't have epigenetics repeated for many children. For some groups, we don't have antibodies repeated for many children except few groups, so it's difficult to reconstruct that. Some of the things that we have done is trying to understand which is the relation, how to integrate these multiple layers. And then we have done this for a couple of biomarkers. One it was AL1, RL1 that we show here, and then for these biomarkers we had the gene expression, we had the epigenetic, we had the SNPs, and we had the phenotype. And what we have found in these biomarkers is that there is a close regulation between the gene and the chromatin for the circulating biomarker, but there is no relationship with the phenotype. So this is a very micro approach. What you would like to have is to have the overall picture for integrate. I think this is one of the things that we want to do in the new project. For some of the environmental exposures, for instance, for the smoking, we have found that the smoking is related to asthma, maternal smoking, but children passive exposure to smoking is not, suggesting that maybe it's maternal smoking who relates through epigenetics maybe to, because there is a big impact in methylation. So we have shown a paper on that with another consortium. So I think that we are in the process of trying to, first, to capture enough data from these different layers into our studies, and then to develop the integrative analysis. Obviously, the dream of the just user, I mean, how you describe it, the black box, just from A to B, so just this magic solution from an artificial intelligence black box would be something like this, but probably we are far from this. But this is the way we are looking for. And I think, again, probably will be a lot of new understanding from, again, I don't want to dismiss the importance of the micro approach. I think we need much more micro approach. We have plenty of findings that we need to fully understand and integrate. I have seen that there is another speaker talking about ATP, energy and the cycle of energy, and by the way we have identified the level of CK, circulating creatine kinase, in blood is a strong predictor of decline in lung function in these children, and we don't know anything about the mechanism. So it's we need to understand these things. But for me, the message is it's plenty of people trying to understand these things in a very refined phenotypes or experiments. There is an opportunity that it's not enough exploited with the multimorbidity. And in the new study, we have integrated metabolic markers looking for cardiovascular risk factors in children.
Yeah. Okay. So thank you very much for this very nice presentation. By the way, Baldo Oliva is one of the speakers of the VPH Summer School. Right. He will talk on Thursday. So if you have questions for him related with Josep Maria talk, you can write it down and ask him on Thursday. The question I have is, when I saw then the map of the different cohorts that you used, I had the impression that it was very urban-centered cohorts. So up to which point this brings biases, no? And because then, of course, so you raise a question. So defining whether epigenetics is important, it's difficult. But then, if you think of designing different cohorts, maybe cross-country specific, maybe urban-centered, etc., do you think you could have enough material and enough tools in order to, from the data, tackle then these specific questions?
Yeah. Well, this again is a very important issue. As you say, you are right. There is a bias here that it's a urban, high-income country bias. This is the cohort for which we have the data, and also is the way that funding science consolidates or dilutes the biases. And in the Horizon program, there is I mean, you need to put European countries, very difficult to put, and you are definitively not funded if you put low-income countries, unless you go through different sources, that is EDCTP or so. But this is a problem, and this is a problem for these particular diseases for several reasons. One is because there is a striking, probably rural, urban extreme phenotypes. With this I mean, when you look to rural areas in Africa, there are several studies, the prevalence of allergic diseases may be 0. If you go to some communities in high-income countries in Europe, you may identify communities in which prevalence is 0. And these communities are basically families running farms in Austria, Germany, Switzerland. So we have very good studies, extremely good, showing that if the children in these families have been exposed to the stables during the pregnancy, most especially, they develop no allergy. Okay? The reason for which we still don't know. It is suspected to be something, maybe a bacterial byproduct, an endotoxin, but it has not been shown so far. So this means that probably these communities reflect, both in Africa rural and in the farms in Europe, they probably reflect the most prevalent environment in 200 years ago. And now we are in another extremely different environment, that is the one in our rich urban areas, or not so rich. I mean, and then we are doing, so we are trying to understand this, but probably, this is a key point, if we could be able to integrate areas in which still this has not happened, we can have the opportunity to see how these networks start to be disturbed, and in relation to what, to which exposures. So this is one important bias. The other bias is that the rural-urban, the urban-rural, even in low middle-income countries, in a way that, what is the rural environment in Spain, or in Italy, in Greece, or in Sweden? And this is not represented in our studies. Our societies are more urban, and in our countries there is few studies looking to the, when you put together the available evidence on asthma, and you look to urban-rural differences in asthma or in allergy in Europe, for instance, there are very few differences, not much, surprisingly. So probably the rural environment has become in the last 50 years also complex and urban in a way or another. Okay, but you don't see many differences. So I think how integrate this in these designs, it would be, and there is an opportunity for perhaps targeted studies too. This is one of the things we are trying to do, to develop research. We are collaborating. We have a center which we have a strong relationship in Mozambique, and we are doing research in Bolivia and in Morocco, and we are looking, but again, funding science in these special multinational settings is a challenge. It's not yet there.
Thanks for the inspiring talk. I'm sorry, I think it's a basic question, because I don't know about this puzzle which you are trying to resolve.
These are the more difficult ones.
Yeah. You mentioned in the last slide regarding heterogeneity of allergic diseases. What do you mean by heterogeneity? I mean, like if we are going to model some electrophysiological point of view, we take endo, mid, and epi, and different proportions of endo, mid, and epi. We decided heterogeneity based on those analyses. But what do you mean by heterogeneity in allergic diseases? Sorry.
Well, the specific meaning of heterogeneity in my slide, it means these diseases share two characteristics. One, they are heterogeneous. Okay, so when you say asthma, there are many different types of asthma inside. Okay, so there may be transient asthma, maybe persistent asthma, maybe food-related asthma, it may be drug-related asthma. So they are heterogeneous. They are not simple. Okay? You may have asthma along your life, and perhaps you may have one type of asthma in one period of your life and have a different type of asthma in another period of your life. Okay? For instance, some of the research that we have developed has been very successful in measuring and analyzing occupational asthma, because the workers are exposed to substances, and there are hundreds of substances that we know can produce asthma. When I say produce asthma, you know that this means if you have asthma, it makes your asthma worse, showing that there is causally related to asthma from nothing to asthma, because that is much more tricky. But occupation, so you may have occupation one part of your time, this is going to change your asthma, then you retire, then your asthma changes. So this, for me, means heterogeneity. The traditional, I mean, the mainstream of approaching heterogeneity is let's to separate them, okay? Let's to separate different, so there have been influential editorials saying, let's stop talking about asthma. Okay? Let's to separate different entities. And my point of view is, if you do that to resolve complexity, you create another problem. Sorry, if you do that to resolve heterogeneity, if you want to resolve heterogeneity, separating these entities in smaller and smaller and smaller groups that you expect to be more homogeneous, and more homogeneous you mean all those affected, there is less variability, okay? Then you create another problem, that you are losing the interconnectivity of many diseases. Okay? And this is what I think is new in my message. And then this second label is not heterogeneity, it's complexity. That I assume is a very in a specific word. Okay? But we say these are complex heterogeneous diseases. When we say there are complex heterogeneous diseases, in general we want to say that.
Sorry, thanks. And so it means heterogeneity varies with age to age, with country to country, with sex, etc. So it means if we will try to incorporate these features, so we are more close to the results or accurate results.
Absolutely agree with you, yes.
Okay. Thank you very much for the presentation. Yeah.
Thank you.